Hi, my name is Łukasz Januszkiewicz and I'm a research audio engineer at SoftServe. I have been working with audio technologies for more than 10 years now, and a big part of my work was concentrated around the spatial audio, mainly touching aspects such as methods of capturing spatial audio, coding techniques. However, recently my activity is more related to the spatial audio rendering. So one of the spatial audio techniques that I am most familiar with is the Higher Order Ambisonics, and today I would like to tell you about some of the technical aspects of HOA and potential benefits of using this approach to spatial audio in games. Before I start, I wanted to make a short introduction and explain why do we care about how the sound is being processed and presented to the listener. So, since the beginning of human existence, people were looking for effective ways of communication. And as we can imagine, it started with some kind of verbal communication or gesticulation. And this is a great way of passing the thoughts and messages to each other. However, it has also its limits. So people had a need to store the messages over the time so they could be also received by people present in different place and different time. So this is how they invented the communication with pictures or hieroglyphs. And eventually writing and reading. So from now on, the messages could be stored and passed to future generations. Over the ages, the development of technology was progressing, but the needs of more and more effective communication were also born. And that allowed people to create new ways of storing and passing verbal content. So we could start here with radio that first used mono and then stereo sound, but people wanted something more than just passing the sound. They wanted to allow the receivers to immerse in the whole sound performance, to feel the space and real life experience as they were at the place and time of the event. So this is how they created spatial audio, and now I would like to take you for a short overview of the spatial audio techniques with a little bit more focus on the higher order ambisonics technology. So here is the agenda of my presentation. I will start with short description of well-known spatial and non-spatial audio techniques, focusing on two aspects. The first aspect is presentation layouts. So in general, how the sound can be reproduced and delivered to our ears. The second aspect is production of audio. So what techniques are used to produce spatial sound, and what is the representation of spatial sound. The core of my presentation is definition of higher order ambisonics, where I will explain to you pros and cons of this technology, what kind of formats and conventions can be met when dealing with ambisonics, how to produce ambisonics content, and how to render ambisonics content into different presentation layouts. In the next section, I will explain what could be the place of ambisonics in game audio, and I will summarize the presentation with some sound examples and demos. So let's start with simple definition of spatial sound. So spatial sound in general allows us listening sound along with its different properties, and we could list here direction of arrival or movement of the sound objects that are present in the captured sound field. We could feel the distance and the intensity of the individual sound objects. We can perceive effects such as reverberation, Doppler effect, and other effects. Sometimes we can also meet another term used in the context of spatial audio, and that is 3D audio. So this term is frequently used for even stronger expression of that the sound can be heard from all of the directions, including top and bottom. So the user can be immersed in the sound performance. And as you can imagine, there are multiple approaches to produce and render spatial audio. So now I would like to discuss the rendering and listening of spatial audio. So how can it be presented to the listener? Just for the reference, we could start here with the monaural audio, where we have a one audio channel, one loudspeaker setup, So there are no spatial cues. The audio is reproduced only with one speaker. This technology was introduced in 19th century and it is still in use in applications where there is no need to send something more than just verbal communication. And first video games also were using mono sound, and it was good enough for that kind of purposes. A very basic spatial audio setup is a stereo setup. We have 2 channels and 2 loudspeakers here, and we have also a limited spatial sound experience, mostly provided in front of the user between the left and right speaker. This technology was introduced in 50s of 20th century and is still widely in use, mostly in home stereo setups and TV sets. Another worth to mention setup is a surround audio, where the spatial sound experience is extended so it covers full or almost full horizontal space around the user, mostly due to the fact that we have more than 2 speakers, usually 5 or more, that are placed on the horizontal plane around the user. This technology was introduced in late 20th century and is still widely in use, for instance, in home cinema audio systems. An extended version of surround systems are the so-called immersive speaker systems, that they are capable of reproducing a multi-dimensional sound field, mainly due to the fact that we have, instead of one horizontal plane with speakers, we have additional 2 layers, a bottom layer and a top layer. So the total number of speakers is much higher. For instance, here we have 22.2 system depicted. This technology was introduced at the beginning of 21st century, and it is widely used in professional cinemas, for instance, Dolby Atmos or DTS. And last but not least, headphone playback. So similarly to stereo setup, headphones require 2 audio channels, and indeed in most of cases they are used to listen to the content that initially was created for the stereo systems. However, there is a spatial audio technique called binaural audio that is used for creating spatial audio content specifically for the headphone playback. And this binaural audio and headphones can provide a real-life experience of hearing sound. So before we go on, I would like to make a short pause and invite you for a short demo where you will listen to the comparison of the same audio content captured in Ambisonics format, but rendered for different presentation layouts and played via headphones. So please put on your headphones and listen carefully to the demo. So I hope you enjoyed it and you could feel the difference between mono, stereo and binaural audio. As a matter of fact, my voice now is also captured with an Ambisonics microphone, and it is binauralized, so you could hear me well via headphones. And I will demonstrate you some other features of that comes along with Ambisonics later during this presentation. Okay, so we have discussed the most known speaker arrangements and presentation layouts of spatial audio. So now I'd like to discuss how the spatial audio can be produced and in what kind of form it can be represented. So let's start here with the most known channel-based audio. So in channel-based audio, the audio content is mixed and represented as a specific number of audio channels. So the content is already prepared. The layout of the presentation layout for this kind of content has to be known before we start to produce the audio. So the producer needs to know if he creates the audio for one channel, for two channels, or for surround audio where we have, for instance, 5 channels. In that kind of spatial audio representation, we have a very limited interaction. So the end user can only change the balance between the specific audio channels or mute a specific audio channel. Basically, there is no more interaction with the content. Fortunately, there are down mixing and up mixing techniques that allow to go from one channel setup to the other setup. For instance, it is quite easy to go from stereo audio to mono audio. Going from stereo to surround audio is a little bit more complicated process, but it is also possible. Another well-known method of producing spatial audio is object-based audio. So in this approach, the audio is represented as a set of sound objects with some associated metadata, such as position of the sound object, directivity pattern, trajectory movement, and other properties of sound properties of sound object. This kind of technique already requires the so-called rendering or decoding before it will be presented to the user. So on the user side, we need to have information how many speakers or if he is using headphones. So what kind of presentation layout is going to be used, and then the renderer is processing the sound objects along with the associated metadata in order to create a proper audio signals that will be derived to the speakers or headphones. So, for instance, for immersive speaker layouts, there can be used algorithms such as vector-based amplitude panning. For speaker arrays or soundboard, we have a wave field synthesis algorithm, and for headphones, mentioned already, binauralization. This representation gives us already a great interaction with the content, as depending, of course, on the functionalities provided by the decoder or the renderer, we can interact with specific sound objects in our content. And this approach is widely used in game audio engines nowadays. So we went through the presentation layouts and some basic characteristics of channel-based audio and object-based audio. So I hope this have given you a good background for better understanding what actually ambisonics is. So let's start with a short definition. So in Wikipedia, we can find a definition stating that ambisonics is a full sphere surround sound format that, in addition to the horizontal plane, it covers sound sources above and below listener. So I would like to make this definition more technical. So I would say that it is rather a 3D audio format that represents the surrounding sound field with a specific number of directive components that are basically audio channels that carry information about the physical properties of sound. So what is sound field, you may ask? So basically this is a term used to describe the physical changes in air that are characterized by acoustic pressure and velocity. And what we also should know about ambisonics, that is, it is not a new technology at all. Ambisonics was developed already in 70s by British engineer Michael Gerson. So it hasn't been used from the very beginning, because there was no need for such applications. It changed in 90s, where people wanted to experience with extended or virtual reality, and ambisonics quite well fits to that kind of applications. Okay, so before describing some more technical aspects of ambisonics, let me first list some benefits that it brings with it. So from the production point of view, we could say that ambisonics is completely layout independent. That means that during producing the ambisonics content, we don't care what kind of presentation layout will be used at the user side. It is a job for the renderer. In fact, ambisonics can represent the whole surrounding sound field. So it does not focus only on the parts where the speakers will be positioned. It can cover the whole surrounding sound field. This technology is also well developed and described in terms of equations, mathematical equations, and tools that can be used for encoding and decoding ambisonics content. A great feature of ambisonics is that it is a really efficient way to represent a very complex scenes with very large number of moving sound objects. So it is also a great way to capture real and really complex audio scenes. From the rendering point of view, again, a great advantage of ambisonics is that it can be decoded and rendered to any presentation layout. And another great feature is that already in the ambisonics domain, we have a great way to interact with the content with the built-in 3 degrees of freedom control, and I will demonstrate it to you later on. As other spatial audio techniques, ambisonics has also its drawbacks. So from the production point of view, we need a really expensive equipment and complex software tools in order to create ambisonics content. And another drawback is that if you would like to have higher spatial resolution of the created or captured sound field, we need to have higher order ambisonics, and higher order ambisonics means more audio channels, so we need more space to store our audio data. From the rendering point of view, similarly to object-based audio, before we play our ambisonics content, we need to decode it or render it to the specific presentation layout. So from one hand, it is an advantage. From the other hand, it is a disadvantage, as we need another process before listening to this content. Also, higher order ambisonics require more speakers in order to reproduce our sound field properly, and this topic will also be discussed by me later. And ambisonics has a relatively small listening spot. That means that the optimal position of listening is relatively small when listening to ambisonics. We are not supposed to be moving too much left or right from this spot, because we won't be hearing the sound field properly, and the positioning of the individual sound sources can be mismatched. So now let me go through some technical aspects of ambisonics format. So as already mentioned, ambisonics provides a sound field representation with a set of directive components, which are basically audio channels, and they are called spherical harmonics. Another common name for this representation is B-format. So each spherical harmonic, or this directive component, contains or carries specific information about certain physical properties of the sound field. So for instance, zeroth order ambisonics component, which is called W, stores only information about the sound pressure. So it can be compared to the omnidirectional microphone, which captures the sound with the same sensitivity, no matter the direction of arrival is. First order ambisonics components, they already store information about acoustic velocity, and their directivity pattern can be compared to the figure of 8 microphone, which has the highest sensitivity in front and at the back, and it has no sensitivity at the sides. And for these components, this figure of 8 shape is positioned accordingly to the axis Y, Z, and X. Higher order ambisonics components contain information about higher order derivatives of the pressure field. So as we could see on the previous slide, with increasing order of the ambisonics, the number of spherical components also grows. So again, zeroth order ambisonics consists only of one spherical harmonic, which is W. First order ambisonics consists of additional 3 spherical harmonics, X, Y, Z, and we have them here. And second order ambisonics adds another 5 spherical harmonics. So in general, we could describe this dependency using very simple formulas. So we can determine how many spherical harmonics in total will our ambisonics sound field contain. For instance, fourth order ambisonics consists of 25 spherical harmonics in total. So let's go back to the end of the best, to one of the best features of ambisonics, which is built in 3 degrees of freedom control, or rotations in other words. So higher order ambisonics allow for easy manipulation of the sound field, and this manipulation is described by rotations. We have 3 kinds of rotations here. There is roll rotation, which means rotating our head left or right, rolling our head left or right. Pitch rotation, which means leaning our head to the front or to the back. And yaw rotation, which means rotating our head left or right. So this feature is provided with simple manipulation of our spherical harmonic components. Here is an example of first order ambisonics that is being manipulated with some simple trigonometric functions and rotations described by azimuth angle. And this feature is extremely useful in the 360 audio-video content. So, as I mentioned at the beginning, my voice is recorded in ambisonics format, so now I can slowly manipulate the sound field and rotate it so you can hear my voice more on the left side, going behind your head, and now more on your right side, and back in front of you. Of course, you need to wear your headphones properly to hear this effect. So now let's talk about some formats and conventions. So as I mentioned, spherical harmonics or HOA components can be stored as typical audio channels, so PCM data in multi-channel wave files. So when we are processing the ambisonics content, it is crucial to know in what order those spherical harmonics are put into the file or into the audio stream. And we can name here three standards, which is ACN, FUMA, and SID. And similarly, we need to know how the spherical harmonics were normalized during the production process. So that means what gain factors were applied to the specific spherical harmonic components. And we can name here N3D, SN3D, and max and normalization. And here is an example of VST plugin that allows decoding of ambisonics format to different kind of presentation layouts. And as you can see, here we have an option of format, and we have to select what channel ordering convention was used and what channel normalization is applied to our ambisonics content. We can meet some file formats that are designed specifically to HOA, and it is worth to mention here Ambix that uses ACN and SN3D conventions, and this format is mostly supported by YouTube. And there is also an AMB format that is using FUMA channel ordering scheme and max and normalization with slightly modification of W channel. So now let's discuss how ambisonics content can be produced. And one way of doing this is recording the sound field. However, basically the recording of native ambisonics, B format, is impossible except zeroth order, where zeroth order can be compared to the single omnidirectional microphone, so it is possible to capture it. So we have our first order ambisonic microphones that capture sound field in the so-called A format, and this format requires further conversion to B format. Usually, first order ambisonics microphones consist of 4 cardioid or supercardioid capsules. Here is an example of microphone with directivity pattern, cardioid directivity pattern. Apart from first order ambisonics microphones, we have also higher order microphones, higher order ambisonics microphones. So basically those are spherical microphone arrays with multiple omnidirectional capsules, and they also capture sound field in A format that needs a conversion to the B format. Unfortunately, higher order ambisonics microphones have some physical constraints that are related to the number of capsules that are being used in those microphones, and those constraints relate to spatial aliasing or narrow frequency band of some of the spherical harmonics. But I will now focus on these aspects during this presentation. So here we have Eigenmic microphone with 32 omnidirectional capsules, and it is capable of capturing fourth order ambisonics. Here we have Zilia ZM1 microphone that has 19 omnidirectional capsules, and here we have a Core Sound Octomic that I believe has 8 capsules, and it has a slightly different construction than the mentioned before Eigenmic and Zilia ZM1. It is a second order ambisonics microphone. The other way of producing ambisonics content is encoding. So in general, in this process we are panning, encoding our sound sources to the desired position, usually defined in spherical coordinate system using azimuth and elevation angles. And just for an example, I have listed here a set of simple equations that allow to encode our sound source S and compute corresponding spherical harmonics components, that is W, X, Y, Z, with the position defined with azimuth and elevation angle respectively. So this process can be repeated for any number of sound sources, and then the resulting spherical harmonics are added up, and then they bring us our soundfield representation in the form of our spherical harmonics. So now let's discuss the decoding, or also called rendering, of ambisonics. So basically, in simple words, the result of decoding ambisonics into the regular speaker layout with a given number of speakers, we can compare to recording a sound field with a set of supercardioid or cardioid microphones, where each of the microphone is positioned in that way that it points towards the position of a speaker that belongs to the target speaker layout. So here we have an example of a supercardioid directivity pattern of a microphone. What is needed to know here that the higher order of ambisonics we have, the more speakers are needed in order to properly reproduce our sound field. And this can be easily estimated by using a simple equation depicted here. So, for instance, for fourth order ambisonics sound field representation, we need at least 25 speakers in our rendering speaker layout in order to properly reproduce the sound field. And just for the reference, here is a set of simple equations that can be used for decoding of first order ambisonics to the speaker setup, where the positions of the speakers are determined by, again, azimuth and elevation angle. Okay, on the previous slides I mentioned that the higher order of ambisonics we have, the more spatial resolution can be provided. I also mentioned that higher order ambisonics require high enough number of speakers in order to reproduce the sound field properly. So here I wanted to simply demonstrate what is the reason of that. So let's assume that we have captured our sound field that consists of sound generated by two sound sources, S1 and S2, and we have captured it in first, second, third and fourth order ambisonics. And now we'd like to render our sound field into the speaker array, and one of the speakers is positioned at the angle of 180 degrees. So if we are doing first order decoding, the directivity pattern for that position will have that shape marked with the blue line. So we can see that it captures quite a significant part of our surrounding space, and the signal plate with this speaker here will cover mostly source number 1 and a significant part also of the source number 2. But when we decode fourth order ambisonics, we can see that this directivity pattern is much narrow, and it captures actually only source number 1. So the signal that will be derived from fourth order ambisonics and then played with the speaker will contain only audio generated by source number 2. So when decoding for higher order ambisonics, and we would like to have also properly reproduced energy generated by source number 2, we would need another speaker position and the angle of 220 degrees. So from one hand, having a higher order ambisonics give us higher spatial resolution, so we can extract much more detailed information from our sound field. On the other hand, we need to remember that proper reproduction of such sound field representation requires also a higher number of speakers. And finally, as you could already hear, HOA representation of sound field can be binauralized and reproduced with headphones. So I just wanted to list here some two types of binauralization techniques that can be used for that purpose. So first of it is a virtual speaker approach. So basically, as with decoding into the speaker layers, we decode our ambisonics sound field representation to the some speaker setup, and the generated signals are then convolved with a specific subset of HRTFs that corresponds to the position of those speakers. So that is one popular approach, and the other approach is direct binauralization. So our spherical harmonics are directly mapped by means of specifically designed filters into the spatial characteristics of the full HRTF dataset. And just to mention, HRTF is a head-related transfer function that in short describes how the sound propagates from the sound source in a given position to the left and right ear of the listener. So let's now go over the typical applications of ambisonics. So I would start here with the 3 degrees of freedom audio that is also joined with the 360 video content, and that kind of content is widely propagated on YouTube platform, or there is another platform called HOA-ST that contains such recordings, but also in higher order ambisonics, as YouTube provides only first order ambisonics. And the other type of content is the so-called scene-based audio, or audio for VR and AR. So this is basically the audio that is captured from one perspective, from one point, and it provides this feature of 3 degrees of freedom control. That kind of content is being supported by MPEG-H 3D audio standard and will be also supported by MPEG-I immersive audio standard. And the other type of content is 6 degrees of freedom audio, where next to our 3 degrees of freedom, which were pitch, yaw, and roll rotation, we have additional 3 dimensions, 3 degrees of freedom, that is moving forward and backward, left, right, and up, down. So the user here have a full freedom in navigating the sound scene. And ambisonics is used here in such applications where there are multiple sound fields, adjacent sound fields captured or generated, and using special renderers, interpolation techniques, the renderer tries to interpolate the sound fields and allow the user move in between the objects of the captured sound scene. Okay, so now I would like to shortly mention how ambisonics could be used in game audio. So one of the greatest features of ambisonics is that it is a very efficient way of storing a really complex sound scenes with multiple sound objects. So imagine that we have a very complex sound scene that consists of hundreds of sound sources. So instead of processing of hundreds of audio tracks, we can transfer them into the spherical harmonic domain, for instance to the 4th order, and then we have only 25 audio channels that can be further processed in the ambisonics domain. So we have a constant number of audio channels that does not depend on the number of sound objects that are present in the sound field. So that is one approach, and the other approach is actually similar one. However, we can use here mixing of real-life captured environment sound that was captured in Ambisonics domain with some additional artificial objects also transformed into the HOA domain. So those are basically two ideas how the Ambisonics could be used in games, and of course it is worth to mention its capability of very nice and smooth control of this 3 degrees of freedom. Okay, so let's go to the demo section. The first demo actually was already presented to you. That was the comparison of mono, stereo and binaural audio generated from Ambisonics audio. Here you can scan the image and go again to this video and watch it again. Another video I would like to present to you is 3 degrees of freedom audio with 360 video content. I won't be playing it to you now, however you are welcome to scan and go to check it by yourself. And the last one is 6 degrees of freedom content with a fully navigable audio. So basically this is a project that I participated in some time ago, where we recorded Poznań Harmonic Orchestra, and it is an example of 6 degrees of freedom audio generated from multiple adjacent sound fields captured with Ambisonics microphones. So thanks to this representation and special rendering techniques, you are able to walk through the stage and listen to the sound from different perspectives. So please put on your headphones now and enjoy the show. Well, that concludes my presentation. I hope you like the demos and the content. Here are some references and sources of the content where you can find more detailed information about Ambisonics. I will be more than happy to discuss with you and answer some of your questions during the Q&A session. And also feel free to reach out to me on LinkedIn profile. Thank you.